And leading up to the idea of why the torque does what it does and how that's related to energy, we consider a different 100-gram mass at 20 centimeters from the axis of rotation. Now, omega is going to be the same as original, same as it was over here, same as it was when we got this 1.2 joules of kinetic energy. But now we're at 20 centimeters from the axis. How fast is this 100-gram mass moving? Well, very straightforward. We multiply the 2 revolutions per second by 2 pi and so forth. We'd redo the whole calculation and we would end up with 0.3 joules. Here we reason it out just by proportionality. If we're at only half the distance, we're moving on a circle with only half the circumference. And we move around that circle in the same time, so we move half the distance around that circle every second. Okay? We move around the circle twice every second, but the circle has half the radius, and we end up moving at half the speed. Half the speed is going to give us, well, what do we do with the speed? We square it when we calculate the kinetic energy. So it's going to give us 1/2 squared as much kinetic energy. Okay? So we conclude that we have 1/4 the kinetic energy at this position. We also were asked, and we talked about it in class, we didn't write it out, but what would the kinetic energy be at 30 centimeters if a 100-gram mass was positioned at 30 centimeters here? Well, that would be 3/4 of the 40 centimeters, so the radius would be the radius of the path followed by that 100-gram mass would be 3/4 of the radius of the path followed by this one. So every time around the circle we'd go only 3/4 as far. Moving at the same angular velocity, we go through the same number of circles, or the same fraction of a circle, whatever the particular omega might be. So if we put a mass here, it's going to move at 3/4 the speed. It'll have 3/4 squared, or 9/16 the kinetic energy of the same mass here. And if we have one at 1/4 the distance at the 10 centimeter position, it's going to have 1/4 squared, or 1/16 of the kinetic energy. So we see that the kinetic energy of per unit of mass doesn't change linearly. Okay? If we go halfway, we only have 1/4 the kinetic energy that we would have if we went all the way out to the 40 centimeter position. And we have 1/16, 1/4, 9/16, and then the full value. If we were to graph the kinetic energy per unit of mass from here to here, our graph would have a significant upward curvature. So kinetic energy of per unit of mass is not a linear function. It goes as the square of our distance from the axis of rotation.